Hello friends, in this video I am going to solve exercise question from book Topics in Algebra from chapter Vector Space and Modules. Question is, prove that the kernel of a homomorphism is a subspace. Before proving this result, firstly we will recall some important definitions related to our proof. So, first definition is kernel of a homomorphism. So, kernel of a homomorphism, say T, from vector space U to vector space V, is defined as kernel T is collection of all those vectors U in vector space U such that T of U is 0 vector in vector space V. That is, kernel T is collection of all those vectors U in vector space U which under T get mapped to 0 vector in vector space V. And note that these two vector spaces U and V should be over same field F. Next concept is, or next definition is definition of a subspace of a vector space. So let V over F is a vector space and W is any subset of V. Then W is a subspace of V if under the operations of V, W over field F is itself a vector space. That is, any subset W of vector space V will be a subspace of V if W itself becomes a vector space over field F under the operations of vector space V. Now we are ready to prove result. So proof. Firstly, we will define phi from vector space V to vector space U as a homomorphism. Now note that this V and U are vector spaces over same field F. Then kernel phi is collection of all those vectors V in vector space V such that phi of V is 0 vector in vector space U. Our claim is to prove that kernel phi is a subspace of V. Now to prove this claim, we will use theorem which states that let V over F is a vector space and W is any subset of V, then W is a subspace of V if and only if number 1, 0 vector is in W, and number 2, for all vectors W1 and W2 in subset W, and for all scalars alpha beta in field F, we have the linear combination alpha W1 plus beta W2 is some vector in subset W. Now note that clearly 0 vector in vector space V is an element of kernel phi. Because phi is a homomorphism, then from property of kernel, property of a homomorphism, we have 0 vector in vector space V will get mapped to 0 vector in vector space U. So we have phi of 0 vector in vector space V is equal to 0 vector in vector space U, and therefore 0 vector of vector space V is an element of kernel phi. Next, number 2, let V1 and V2 are any two vectors in kernel phi. Now as V1 and V2 are in kernel phi, we have phi of V1 is a 0 vector in vector space U. Similarly, phi of V2 is a 0 vector in vector space U. Then for any arbitrary scalars, say alpha beta in field F, we have phi of alpha V1 plus beta V2 is equal to phi of alpha V1 plus phi of beta V2. This thing follows from, or this thing follows since phi is a homomorphism. Now LHS as it is, this RHS can be written as phi of alpha V1 will be alpha times phi of V1 and phi of beta V2 will be beta times phi of V2. Again this thing holds since phi is a homomorphism. Now phi of V1 is 0 vector in vector space U and phi of V2 is again 0 vector in vector space U. So this linear combination will be 0 vector in vector space U. And so we have phi of alpha v1 plus beta v2 is a zero vector in vector space U, and therefore this linear combination will be an element of kernel phi. And so by this theorem we have kernel phi is a subspace of vector space V over field F, and this proves our result.